The members of this group project are Nina Tedeschi, Rita Rosenthal, Dan Schenkelman, and Vedant Gapwal.
We go to Johns Hopkins University and we're a class of 2024.
We're all mechanical engineering majors, and Nina is a BME major as well.
This project is for 530.232, Mechanical Engineering Thermodynamic Laboratory. The goal of this project was to propose, set up, conduct, and report on set of experiments to characterize the efficiency of a device for choosing. The device tested in this experiment was an 1875 watt hairdryer with 2 speeds and 3 settings with a push-up button. In this experiment, we examined the thermodynamic efficiency of the hairdryer as a function of the hairdryer's temperature settings, speed settings, air inlet, percent obstruction, and ambient temperature.
The intended function of this device is to dry hair. The hairdryer uses electricity from the power outlet to power a heating element in the fan. The fan draws air into the inlet and out of the outlet through the hairdryer cavity and over a heating element. The hairdryer was placed on a support, which was made of plastic cups and acrylic for testing. An anemometer was attached to the inlet to measure airspeed. To measure the power going into the hairdryer, it was plugged into a kilowatt meter, which was plugged into an electrical outlet. To measure temperature, at the outlet, a thermistor and an Arduino was used.
To conduct the test, the anemometer and hairdryer was turned on and a grate was inserted if appropriate. The power meter and airspeed were read, and the temperature data was recorded to a PC. The first law of thermodynamics was applied to create an expression of the input and output energies that was used to calculate thermal efficiency. When the hairdryer was switched between the cold, low, medium, and high temperature settings, it was observed that the efficiency generally increased with the set temperature, which was expected since electrical energy is likely more efficiently converted to heat than to air velocity. As a result of testing at high and low speed settings, the low speed setting was more efficient since half the AC wave gets blocked at the low speed.
The inlet percent obstruction was varied by drilling out various areas out of acrylic circles and placing them between the anemometer and the hairdryer inlet. With these settings, it was observed that thermal efficiency increased generally with the percent obstruction increase. This contradicted initial assumptions of that the air behaves as an ideal fluid and is explained by there actually being realistically an internal velocity volumetric flow rate limit that is approached more and more with increasing obstruction, causing the observed increase in the thermal efficiency. The external temperature was varied by running the hairdryer in various environments, including a freezer, outside, room temperature, and covering it with heated pans to reach high temperatures. It was observed that the thermal efficiency generally increased with external temperature. The recorded freezer trial produced unreasonable around with about 100% efficiencies, and was thus excluded as an outlier. All other data points had some errors, but were not significant enough to impact the validity of the results.